Hi, my name's Anthony Massey, and I'm here to present my digital forensics final project, which is an autopsy plugin that I called Hostage. It's a file ingest module that attempts to identify postmortem crypto ransomware infections by computing file entropy. So, the first thing I'd like to note is, the question would be, what is file entropy? So, file entropy is a way of determining the randomness of bytes in a file. So what I used for this project is the Shannon entropy formula. It's a scale from 0 to 8. Well, it returns a scale from 0 to 8, where 8 is a random distribution of bytes and 0 is a completely non-random distribution of bytes, I guess. So maybe like every byte is the exact same byte, like 41414141 in the case of a bunch of A's, or maybe no data at all. So crypto ransomware encrypts the files on your file system using generally well-known symmetric crypto like AES, or maybe asymmetric like RSA. So theoretically, files encrypted by these algorithms should have high entropy in between 7 and 8, probably 8, because I think that's the indistinguishability notion in crypto theory that should appear to be completely random. So let's get started with a quick code walkthrough, and then I'll show you the module in action, and I'll try to wrap this up pretty quickly because this is like my 5th time recording this. So here's the hostage factory class. This is just like the default, setup for the actual plugin: the name, the description, the version number. The meat of the plugin is in the hostage module class, where I instantiate a logger for debugging purposes. My startup function's blank. I don't need to do anything specifically at startup. Excuse me. There's a get bytes function that takes the abstract file, which is passed in for each file in the file system, and returns a J array of the bytes that make up that file. Get entropy is the next function, which takes the byte array returned by the previous function and counts the distribution of unique bytes in that array. So as you could see at line 83, this if block, I'll highlight that. Hopefully that shows up in the video. I count through each of the bytes in the file. I iterate through each of the bytes in the file and keep a running tally of how many times each byte appears and put it in this list. And then I established a frequency for these bytes by dividing the count over the amount of bytes overall. So each byte has like a frequency percentage. And then for each frequency, I compute the entropy, and that entropy sort of compounds itself as it loops through the file for each frequency for each byte. And then I return the entropy. I got this entropy formula here at line 95 from bearcave.com. It was incredibly useful, and it's really the most important piece of the script here. So the actual main function of the script is this process function. From my previous experience working on ransomware, both with this project and with my research at the FTC, I've noticed that ransomware is one type of malware that you don't really have to go looking for to detect its presence. Ransomware is in your face. Ransomware wants you to know you're infected, and ransomware wants you to think that the infection is as severe as it possibly could be in order to extort money from you. So related to this, I avoid the Windows directories, the program files directory, and the 32-bit program files directory, because I'm confident that this script can help a researcher determine a ransomware infection without ever touching any of these directories, and that definitely speeds up parsing time by, like, if I had to guess, maybe tenfold. It would take like 24 hours. I have a 6700K, and it took like 24 hours for the initial version 1 of this to finish. Once I cut this stuff out and I added some more of this exclusionary stuff to avoid parsing files I didn't really need to parse, it sped up a whole bunch, and now it runs in maybe an hour and a half for a 40 gig ISO. So yeah, I avoid these directories. I also avoid these archive types, because I'm not sure if I stated it before, but when it comes to entropy, compression and encryption are extremely similar. Compressed files will have a similar entropy to encrypted files, So I added a bunch of these known compressed archive types just so I could avoid them in case I found them in the operating system, to not only speed up parsing time, but to reduce the amount of false positives. This is a naive approach that I would like to get rid of once I continue working on this once the semester's over. I feel as if I could find a better way to do this, because as of now, if the ransomware chooses to rename your encrypted files with an extension that matches any of these, all of the encrypted files will be skipped by this plugin. I only know of one family of ransomware called BART that uses the .zip extension, but one is enough for me to realize that if I really want to open source this and maybe try to enter it in a competition or something, I gotta improve on stuff like that. But for the sake of this project, this was a proof of concept on the entropy stuff, so I will get to that stuff eventually. I also avoid unallocated blocks, unused blocks, and things that aren't files for obvious reasons. That's just a waste of time to parse. I get the bytes for each file and I pass it to the getEntropy function. And if the entropy is greater than 7, I put it in a list and show that to the user as a possibly encrypted file. Okay, so let me close out these windows and just load up Autopsy. So one thing I'd like to note is that this, as of right now, it might never be a catch-all solution for saying this is definitely a ransomware infection. But you know, I'll get back to that. Let me start this up. So I'll start this from scratch. So let's call this just demo. Give this a second to load up. So I'm going to load up a clean Windows 7 ISO. It has a whole bunch of canary files on it. Hostage is the only ingest module loaded. I'll let this run for like a minute, maybe even less, just to give you an idea of what it looks like to the end user. So while this loads, oh, alright, it loaded. Okay, so this gets started, and as you're going to see, we show up possibly encrypted files. As of now, it's just JPEGs. These are compressed. I'll need to figure out a way to avoid these other than doing the naive file extension thing, because I really don't like that method, and I don't think it's the best method for the job. So like I was saying before, I think that this will in the future be enough for someone to say beyond a reasonable doubt that your system is infected with ransomware, but it's not there yet. You kind of have to parse through the possibly encrypted files list and get rid of these, or at least know that these files aren't encrypted. It's not hard to tell if they're not encrypted, as you'll see from the next image, which I'll go to now. So for now, I'll jump straight to an infected image, and then I'll jump back to a clean image that finished running. Both of these next two images will be like completed runs. So this one was infected with TeslaCrypt. It's the same exact image as the clean one, just post-infection. So as you can see here, there's about 466 encrypted files. I'll load these up. .png files are also compressed, so them showing up in this case is actually quite helpful because you can immediately see this ransom note. A lot of ransom notes. I think this sample drops them in every single directory. All right, so here's an example of a JPEG that was changed to a .jpeg.mp3. You can see that there's no like picture of minions or any of the other stock photos I had because this file is encrypted. Even for the one that doesn't have the extension changed, which is the exact same file, so I think this is like carved from maybe the shadow files or something. This is also encrypted or deleted. And then there's a whole lot of ransom notes, a whole bunch more of encrypted files. And then there's a few false positives. Like these are all encrypted, these are all ransom notes. I'm just scrolling through these really fast. You probably can't see because of the way this video is going to be recorded, so I'll slow it down a little bit. So here you see a GIF. That's because it's also compressed. these JPEGs got caught up. These GIFs weren't encrypted. I don't know why the ransomware didn't like those. All these JPEGs are done. They're all locked up. So yeah, you kind of get the picture that with a little bit of background knowledge, this is very useful because you can, if you're someone like me or anyone who has any kind of experience with this type of malware or has even just read about it a little bit, you'll be able to tell that you're infected. But I haven't figured out a way to sort of say you are 100% infected without risking being wrong. And that's something I would like to work on in the future. So I'll load up a clean image that's finished running and wrap this up really quickly because I think I'm about going over time. I wanted to limit this to 10 minutes. So I'll finish this within the next minute. So here's a finished clean one. And as you can see, all 128, so there's about 300 less that were detected, but all 128 were false positives for this one. So you see your JPEG, you see the minions, you see these PDFs, which are compressed, these XLSX, a lot of the the Microsoft Office extensions are encrypted. I mean, compressed, I'm sorry. Some of the GIFs from before, which still have that high entropy because of their compression. So removing these false positives is the next step, but I think it works well enough right now for someone, like I said, with an experienced eye to be able to figure out whether the system was infected or not. So, if there's anything I forgot to say during this presentation, I'll be sure to include it in the supporting documentation that I include in my submission. So, thank you for the great semester, and I hope you enjoyed the video.